Welcome to our review on satellites and orbits. So the first thing we actually need to know here then is that when we're talking about satellites, we're talking about something that may either be natural or it could be artificial. So when we're talking about a natural satellite, this is things like the moons, as you can see in the bottom left there. Now the key thing about the natural satellites is that they're made from the same material as the rest of the objects in our solar system. If we think about the artificial satellites, like the bottom right there, these are the ones that have been sent up into space by humans to orbit objects like the sun or planets. So obviously very different from the natural satellite on the left. So what we actually find then, in order to keep those satellites where we expect them to be, then they have to be in what's called orbit. Now we've got two types of orbit that we could use, a geostationary orbit or a low polar orbit. Now natural satellites do have a different orbit from the artificial ones, but we're just going to focus on these two artificial satellite orbits. If you look at the bottom left, you can see a little diagram that summarises the difference between them. So our geostationary orbit is that big circle going around the whole Earth there. Now the whole idea about that one is that the satellite appears to be in the same position above the Earth's surface no matter when you look at it. Whereas the low polar orbit, which is the one that just wraps very close around the surface of the Earth in the diagram, they travel over different parts of the Earth's surface in each orbit. If we look at these orbits in a little bit more detail then. So the geostationary orbit, that will take about 24 hours for one orbit. Now that's important because, as we've said, the key feature of this is that it remains in a fixed position above the Earth's equator. Now, the fact that it takes 24 hours for our satellite to orbit the Earth once also happens to be the exact same length of time as it takes for the Earth to spin on its axis once, hence why they appear to stay in the same position. The geostationary orbit satellites will be higher above the Earth's surface at about 36,000 kilometers, and we use them for communications and satellite TV. So if you think about satellite dishes on houses along your road, then what you'll notice is they all point in the same direction. And the whole idea behind that is our satellite TV satellite is in a geostationary orbit, therefore in one position up in the sky, and that means that all those satellite dishes pointing in that one direction means that they're always going to be pointing at the satellite TV satellite. Second kind of orbit we need to know about, the low polar orbit. This one's got a much shorter time, so only about 2 hours for one orbit there, so they're whipping around really quite quick. And they're much closer to the Earth's surface at about 2,000 kilometers again. Now, the key feature about these is that they actually orbit over the poles, as we saw in the diagram on the previous slide. And what we do is we'll be using these for spy satellites with the military, could be observations, so any of the Google Maps ones, for example, and weather satellites, quite important at the moment. So because they've got a 2-hour orbit and they pass over a different position of the Earth's surface, then what we can do is pick up a lot of information about those areas and create these bigger pictures. So if we've got an object that's moving at the right speed for the distance at which it's orbiting an object, then what we find is it's got a stable orbit, and that's things like our planets. So the distance they are from the sun and from each other, and the speed at which they're moving holds them in this lovely stable orbit so we don't all crash into each other or the sun. Now what we actually find is if we look at the speed at which the planets in our solar system are moving, the further from the sun we go, the slower the planets are actually moving. Now the reason behind that is because when we go further from the sun, then the pull of the gravity from the sun is going to be lower, because as we know, when things are further away, the pull of gravity is less. So what we actually find there is that it's only got a small force changing its velocity. So if we consider Neptune as an example here and what effect it would have if it was to move at different speeds. So if Neptune was to randomly speed up, then what we find is that that gravitational force would actually be too small to keep it in orbit. So instead it would end up flying off into the depths of space. Whereas if Neptune was to slow down for some reason, then what we'd find is that we'd no longer be able to maintain that fixed orbit. So what we'd find is it would start to accelerate towards the sun because the pull of gravity is stronger than the force pushing outwards. Hopefully by the end of this video you can now explain how the force of gravity can help keep an object in orbit. You can explain why the force of gravity changes the velocity of the object but not the speed. And we can also explain what happens if the speed of the object actually changes when it's in orbit.